Trying to get the link so that I can share it to Facebook. Okay. All right. Just waiting for people to get here. Let's see. What's going on? Is it still working? Okay, I think it's still working. Good. Okay. Okay, so just I think I see someone is here, so just put your question or comment. Eventually, I know some things I want to cover are recursion and a bit of graph theory, but I don't know. Yeah, can't really tell who's here. I think there might be a delay too. Hmm. Okay. Well, I'm gonna plug into Ethernet so that it doesn't do that again. I think it just dropped out. Okay. Okay, I think. Oh, but now there's no one watching. Okay. Um. Hmm. All right. So there's someone watching. So I'm just gonna go ahead and get started, I guess. I want to make sure that I'm not limiting the chat to just like paying people or something. I don't think I am. If you're watching this, I'd really appreciate it if you just say like something in the chat. Um, yeah. Okay. Um, so I have a whiteboard, so I might use that. Um, but yeah, I think I'm gonna use that. It might be useful. I'm gonna go over recursion first. Okay. So recursion. Um, let's see. Okay. So let's see. You can kind of see that. I'll like go like that to make sure you guys see that. But recursion has to do with um, algorithms. Uh, so, and an algorithm is just a set of instructions on how to do something. So usually you think of like computers because in computer science, um, you're basically when you're writing software, you're implementing algorithms, um, telling the computer how to do something. So it's a set of instructions. So in the proof, one of the key parts is I define a function, um, and I'm thinking about whether I should call it a function or an algorithm or what, because it's more than just a set of instructions on how to do something. It's a it actually has it evaluates to something. So it in computer science terms, they would say it returns a value. So like um, for example, an example of an algorithm that might return a value um, is if you were given what's it good? Okay, so if you were given a string of characters and uh, you had to return either a yes or a no, and you're supposed to only return yes if there's the same number um, of like left brackets as there are right brackets, um, and so an algorithm for that might be like you start at the beginning of the string, and every time you encounter a left bracket, you add one to some counter, and every time you encounter a right bracket, you subtract one from the counter, and then at the end, you if the counter is equal to 0, then you know that there must have been the same amount of left and right brackets. Otherwise, so then you return yes. Otherwise, you return no. So that's the basic idea of a function and of returning a value. Um, Basically, what I did in my proof, I kind of handled it in a very computer sciencey way because I'm basically treating like I mean if you know computer science, like this it's very easy for me to explain it to you. I'll try to explain it to you how I would explain to someone who knows computer science, and then maybe you guys can like in the chat explain or say which parts you don't really get. But basically, I'm kind of treating it like as if there was a class called proposition, um, and a class is basically like it's a group of things, and it can have a superclass and a subclass. The superclass the superclass and subclass relationships are described as like as is-a. So basically, a subclass. If you have a subclass and a superclass, the subclass is a superclass. So, for example, human and mammal. Uh, Human is a subclass of mammal because all humans are. You can think about it also in terms of sets. Like all humans, human is a subset of mammal um, because all humans are mammals. But yeah, all humans are mammals. It doesn't have to be a proper subset, so it could be um, like I don't know the same set. But anyway, you can think about it as a proper subset for now. So human is a mammal, so it's a subclass of mammal. So in the same way, I was treating it like in my proof, like there's proposition is a superclass of um, well, it gets kind of weird too because yeah, it's actually one of the big problems of using classes because I want to basically describe uh, like a proposition can be a conclusion or it can be a premise or it can be both. because we're looking at it in the view of someone's actual beliefs. So, for example, um, the uh, the fact that let's see, the fact that I see this like cleaning cloth, um, that could be a conclusion and a premise, because I could conclude it from one of the proofs that I have in my belief system, like um, there's the fact that I can see it. So um, some of the premises I might use in that proof are I exist, um, it exists. I might define what it means to see something, and so forth. And then um, I might use that fact, the fact that I can see it, um, to prove something else. Like I don't know. I can see it, and everything that I can see, I can touch. Therefore, I can touch it, or something like that. Um, so in that case, that's an example of it being a premise and a conclusion. So basically, maybe I should use it this idea of a class. Getting kind of off topic here, but basically, my goal is to cover recursion, um, and I only really wanted to. Uh, I only really wanted to use this idea of a class to explain the idea of a property, um, because I'm basically using that um, in the proof, where I get all the premises from a conclusion. So let's go over known of a claim called C. So I'm going to write it out because I'm pretty sure I have it from memory. I'm going to do it kind of in a C style programming, except I forgot the return value. Should be returning a boolean. But so if you can see that, it's the beginning, and then so basically claim here, that is that's telling me um, what kind of variable C is, or what type, or what class. That doesn't look like a class, but what type it is. So um, later on, I can like say, okay, and basically this is what I did in the proof. I did like maybe I don't know, C/Java. I'm spelling it like Java, but what did I do? I did uh, for claim. I'll call it P for premise in C dot premises. Okay, so what this line does is so since all claims have a set of premises, it might be an empty set, but and in which case this would just skip; it wouldn't do anything. Um, but basically, since all claims have a set of premises, it grabs that set, and then for every um, for every element of that set, which we know is going to be a claim, since all premises are, oh, I'm using claim. whatever. I use claim and proposition interchangeably. Um, but basically, I'll just use claim from now on because I'm using it in here. Um, but so it gets all the premises from C. So what this evaluates to is the set of all um, premises in like someone's set of beliefs, or because I think I explained that a little bit better in the proof, but I created kind of a representation or an interpretation of um, of a directed directed graph where you interpret the see, now we're already getting into graph theory. Well, they're gonna come together. So um, you interpret a directed graph at the so directed graph is basically just like nodes or vertices. Nodes and vertices are the same thing, and edges. So these dots I'm drawing represent nodes, and then I can draw an edge, but each edge is a directed edge, so it has a direction to it, basically saying whether it's pointing um, from A to B or B to A. And you can have like two, like I can have an edge from B to A, from A to B, and from B to A. But let's just create this thing here. Okay. So here is a graph, a directed graph with the edges from A to B, from B to D, from C to A, and C to D. Um, so basically, I'm just kind of proposing a different way of constructing it, and a different way of interpreting it. So the different way of interpreting it is saying that um, basically A is a premise that is used in a proof that has B as its conclusion, and B is used in a premise as a premise in a proof that has D as its conclusions, because these are all these nodes are claims, propositions, same thing. Let me see. Okay, I still got someone watching. Um, so um, right. Hopefully that's not just my own, since I have it up. Um, so right. These are all propositions, and the arrow indicates that the thing that it's pointing to is a conclusion, and the thing that it's coming from is a premise. And the way that you construct it, which is the other thing I was going to mention, was that you start with all the things that you claim to know, and then you, well, you could start on either end. You could start at all the things you claim to know, or you could start at your axioms. If you start at your axioms, it's going to be even more obvious that you can't know anything, because axioms are essentially faith. Either you call it faith up front, or you masquerade it with self-evident, which does not make sense. And I encourage you to come up with a statement that is self-evident, that you think is self-evident. If you put it in the chat, I will tell you why it's not self-evident. But okay, so that's kind of my interpretation of the graph that I'm using in the proof. And so each one of these would be a claim, right? And so basically all the premises thing does is say, okay, um, what are all the nodes that are pointing to, let's say I passed in B for this function. Then it asks what are all the nodes that point to B. So in this case it would just be A, but it could have been also C, and it could have also been D. And actually I'll use this as an example to run through this. Okay, yeah, that would be a good idea. So what it does is, okay, so now we have this thing set up, and what it does is, here's where the recursion comes in. Recursion is really a simple thing to say, but it can be kind of difficult to comprehend at first. Basically, what it does is it says, okay, well, if one of the premises is not known, then then if one of the premises of the claim that we're looking at now is not known, then the claim that we're looking at now is not known. So it's if I'll do it kind of yeah. If P or sorry, if known of P equals false. So if it's not known, then return false, right? So it's going to go through all the premises, and if it turns out the known of P is false, then it returns false. The one problem is that this actually might go into an infinite loop, and we might actually see that down here. But obviously, if it goes, and I'll show why when it goes into an infinite loop. That's the same. That just means you have circular logic as your ending point instead of faith. But okay, so it goes through all of them. If it turns out one of the premises, probably can't see that, but if it turns out that one of the premises is false, is not as false. If it's not known to be true, then this claim that we're looking at now is not known. Okay, and then if it goes through all of them, which it never will, but if it goes through all of them without ever saying that it's false. Oh, also I should say, right, if C doesn't have any premises, then it is an unknown claim because, like I said in the premises to my proof, the last one, it said the only way to justify a belief in a claim is through a proof, and all proofs have premises. So it's basically, yeah, it's when you run into a claim that you don't have any premises for, you don't have any proofs for, then you don't know that claim to be true. So I guess I should have put something at the beginning that said, like, if C that premises dot count equals 0 or whatever, but I guess I can add that in now. So it goes through. It's be really inefficient program, but so okay, so if I'll add that in now. C dot premises. I'll just say like equals null if it doesn't exist. Then then return false. It's not known. And then if it gets through all of that, if it gets through all of that, then it can return true. But it won't. It won't ever get through all of that. And we can show that. I mean, I'm sure there's a way. I'm trying to figure out how to. But I'm sure there's a way you can show how it won't work for any case. But okay. Almost forgot my semicolons. Okay. So now we're going to, and I might as well just make it a better, more clear graph that I'm going to use as my example to run through this. So I'll just keep it to 4 nodes, and I'll just kind of randomly add, or maybe I'll make it look more like what a real use case might be. I'll do that. So I'll have like a couple premises, A, B, and C, and then maybe A and B, kind of create one, and then maybe B and C make one. And maybe A and this newly created one, make one, and this one. That's okay, that's pretty complex. Yeah, let's do that. Okay. So this is which B, C, D, E, and F. Okay. So this is what we're going to use, and we're going to actually run through this as if we were the computer that was doing it. So, okay, we'll start with. I mean, it's easy to see how if you start with A, B, or C, you're going to skip this part, and then the premises will equal null, so you return false, and it won't be null, right? That's pretty easy to see. But what's harder maybe to see is why F is not known. Did I say false before? I meant unknown. And actually turns out that all of the premises of a claim, if they're if a claim has premises, then all of them are not known. So, all right, let's start with F. So, and we'll just go from like top to bottom whenever it comes to choosing what order to do the premises in. So F. Okay, so we're trying to do known of F. Now, actually, there's a cool little way you can write it down to keep track of stuff. So known of F. This is kind of like keeping track of what we've called so far. So known of F. All right, we're in our known of F call right now. So the first thing we're going to do is, all right, we're going to go for claim P in premises. Okay, so F dot premises. What is that equal to? That's equal to D, A, B, and E. D, A, B, E. So, because those are the ones that point to it. So, let's start with D then. So now we're going to call known of D. Okay, so now we're here. Known of D. So known of D. Okay, now we're in our known of D call. And so what are we going to do? We're going to get the premises of D, which are A and B. Might take a while. So the first thing we do is, first thing we do is call known of A. So now we're in our known of A call. And as I just showed, known of A is equal to false. But I'll show it again. So known of A. We skip through the for loop because there are no premises. And then since there are no premises, we return false. So known of A is false. We'll just say Uh, so yeah, we'll just, I guess, write false here. All right. So now we're back at our known of D call. We're gonna go one up. So we're back at our known of D call. So the next thing that we were gonna do in our thing was in our call of known of D is to call known of B, and it's gonna be the exact same as known of A since they both don't have premises. So I'm gonna have known of B, and that's gonna be false. And then, okay, okay. So we finished our known of A, we finished our known of B. That finishes our for loop for our known of D. So now we're on known of A again, because A was a premise for F. So we're back at our original call of known to F, of F. And as we already found out, known of A is false. So we'll just write out here, known A false. And then we have, so we finished our known of A. Now we have a known of B. So known of B, as we already saw previously as well, is false. So by the way, the way it really would have worked is it would have short-circuited, or not short-circuited. That's like a bad. It would have the first time we would have never evaluated known of B in this case, because as soon as we found out the known of A was false, we would have gone back and said, okay, well, known of D is then false, and okay, then known of F is then false, because, and as a matter of fact, we might as well do that. So, yeah, it's going to be simpler too. Okay, so we called known of F, all right, and that made us, this is our known of F, and then, so claim P in F dot premises, so because we passed in F here, so that's F now. So F dot premises, and then the first thing we checked was D, so the first thing in the set of premises is D, so we call known of D now. So this is D now. And the first premise in D's set of premises is A, and A has no premises, so this actually returns false. And then once A returns false, we were just here, right? We were just evaluating all the premises of D. So since known of A is false, then known of D is false. And now we're back up. We were just evaluating the known of D because it was the first premise in the set of F's premises. So known of F's premises. So it turned out to be false. So then we return false for F, and that's how F is not known. And I think if you understand how that one worked, you can pretty much understand how it would work for every single one. In this particular belief system thing. So that the whole thing where you call known of, like where you call known within itself, makes this a recursive function or a recursive algorithm. So yeah. Yeah. So I covered recursion, I think, and I covered my use of the directed graph. Um, not getting any interaction, so I'm starting to suspect that I actually am the only one watching this, just because I have it up on the YouTube thing. Um, so if there's anyone here, um, yeah, I don't know. If there are any questions, hmm, maybe I'll just uh, I'll probably just um, yeah, okay. I think the link will still work after, so I guess YouTube will upload the live stream, uh, and then you guys can watch it there. So I'm gonna go ahead and um, I'm gonna go ahead and end the stream.